Welcome to Siemens EDA podcast series on 3D IC design, brought to you by the Siemens Thought Leadership Team. In our 7th podcast on 3D IC reliability, we discuss the impact 3D IC design has on device reliability, ranging from understanding thermal interactions between devices to the related thermomechanical stress that can lead to warpage and design failure. Today, we will discuss the impact that 3D IC design has on test, ranging from design for test, or DFT, and IP testing, through complete multi-die packaged product test. I am pleased to introduce my special guest, Joe Rainick, who is the Test and Product Engineering Manager for Siemens EDA. Welcome, Joe. Thank you for taking the time to talk with me today about the 2.5D and 3D IC tests. Before we dive into the discussion, would you mind giving our listeners a brief description of your current role and background?
Sure thing, and thanks for the introduction, David. Thanks, everybody, for inviting me here today to talk to you about multi-die, 2.5D and 3D IC test. Just as background, my current responsibilities include Product Engineering Manager for the Tessent suite of tools from Siemens EDA, and that's a division of Siemens Digital Industries. As background, I have 37 years of direct experience in ASIC design, optoelectronics, design for test, IP test, and silicon bring-up, and EDA. My prior experience was at eSilicon, which is now part of Marvell, and Bell Labs. Currently, I'm responsible, as I mentioned, for product engineering of the Tessent DFT tool suite.
Very good. Joe, can you give us a brief overview of how DFT and IP tests fit into the design and manufacturing phases for 3D chips?
So first of all, DFT means design for test, which is structured logic that we insert into the chip during the chip design phase. That DFT logic just makes the chip easier to test while forcing the chip into all possible defect states. So hardened IP cores may also be inserted there during the design phase, and these cores may also have DFT and IP core specific features that need to be integrated into the overall DFT and test access scheme. So for 2.5D and 3D, we have extra design steps to insert logic that provides test access to each of the dies, including new capabilities for die-to-die interconnect testing. Besides logic insertion, we also need to thoroughly verify the DFT and test logic before creating the chip masks and sending the part to manufacturing. So that whole verification phase is a big step. We also need to generate the DFT and IP test vectors that will be applied to the chip during manufacturing test. So on the manufacturing side, we have two major activities. Wafer test, which we also call KGD or known good die test, which includes the die level test that we created in the design phase, and package test that includes those die level tests that we did during KGD and the specific tests for 3D test access and die-to-die interconnect testing. So that's the main difference between standard just fixed 2D regular chip test. With 2.5D and 3D, we add the feature of die-to-die interconnect test.
Fascinating. Joe, there's been a great deal of growth and development around advanced multi-die heterogeneous packaging over the past several years. Aside from design and analysis, what challenges do heterogeneous assemblies need to overcome for DFT and production test?
Yeah, so first of all, a little bit of a definition. In previous installments of our podcast series, we covered SIP, or System in Package architecture. So when you hear us say SIP, it's talking about having multiple dies inside the same package. So basically, we're putting a system in the package. That's comprised of 2.5D, which is like MCM on steroids, and then 3D, which is stacked die. So both 2.5D and 3D require die-to-die interconnect test and the individual die test that we talked about to be repeated from wafer test to the package level, and they're typically run at different temperatures. So the keys to accomplishing 3D test are, as mentioned, test access. So how do I initialize and test just that middle die in the 3D stack? Or how do we initialize and test just the I/O buffers and die-to-die interconnects within the SIP? And then on common interfaces, how do we apply scan pattern data to just that middle die in the stack and test all of the chip digital logic? So we need to make sure that we have common interfaces between each of our dies so that we can communicate cleanly between the dies. We also want to expand the DFT planning and collaboration to include physical design and package engineering. So for example, SIP test IO spec needs to be defined at the interposer for 2.5D or through silicon via level for 3D. We may also add sacrificial pads for known good die or KGD wafer probe. We'll talk a little bit more about that later. And common die-to-die test interfaces are required for all chiplets. So compatible die selection criteria and binning for dies from different processes we need to be aware of as well. We may be mix and matching parts from 7 nanometer, 3 nanometer, 5 nanometer, 14 nanometer on the same package. And so we need to make sure from a timing perspective, for example, that these parts are compatible. So we have to come up with strategies for doing that. And then die level test access to the package IOs is needed for running the full suite of the SIP level package test, burn-in reliability screening, and split corner characterization to see at what extremes of process, temperature, and voltage can we run the test. We also need to be aware of thermal and power issues that we talked about in our 7th podcast. So for example, IR drop inside the package, any thermal excursions that could be going on during test, and test activity factors can often exceed functional activity factors. We need to be aware of that. So packet-based scan from non-overlapping scan clocks is also a useful technique for keeping IR drop under control. And a little shameless plug, if you look at poster 18 at the 2022 International Test Conference, it's in the proceedings there or online. You can see a good paper on IR drop and control using packet-based scan. So then the use of hierarchical DFT for 2.5D and 3D package assemblies or a mixture of both in the same SIP can exist. So we call that 5.5D actually. A good example of that is HBM, where we have 3D stack and 2.5D dies, host die on the interposer. So 2.5 plus 3 is 5.5. So we get that from the IEEE 1838 3D test standard. Adherence and support of interface standards is really important, especially for 2.5D SIPs. And that includes emerging and established standards like HBM3, UCIe, bunch of wires, sometimes called BOW, Open and OpenHBI. These usually include special die-to-die PHY tests that need to fully test these interfaces, so often included with the IP core itself. And these PHYs often incorporate new test and reliability methods like IO-BIST with lane redundancy to repair defective connections between the dies. And these methods can be also independently implemented at the chip level. We have to be aware of enhanced DFT planning for the IO spec and interface of multi-die and chiplet packages. And we have to also be cognizant of comprehensive known good die testing at the wafer chiplet level to provide fully tested bare dies for assembly into the system and package. So these fully tested bare dies are a real challenge because the wafer probe level can be very noisy and power limited, but we have to run the full test program at the die level and make sure those bare dies are fully good before we're trying to assemble them into a multi-$1,000 package, right? We don't want to be throwing away those expensive parts. And then we need closer collaboration with system level testing. So we truly are moving systems into the package. And so, for example, for 2.5D, we need to run board level die-to-die interconnect testing inside the package using IEEE 1149.1 boundary scan, which was typically only run at the system or board level in the past, but now we're doing it inside the package. We also need to do die-to-die at-speed interconnect testing. So in addition to things like IO-BIST and lane repair, we may have USR and XSR SerDes. We may have things like at-speed scan as well. Yeah, so that's pretty much the things that we need to be aware of for 2.5D and 3D test.
Interesting. Given the comprehensive nature of ensuring high defect coverage and reliability, what DFT and IP test methods should the DFT and IP test team implement?
First of all, early in the ASIC or chiplet I/O development phase, we need to be able to generate and insert a primary tap, secondary tap, as well as what they call FPP or flexible parallel ports, following the IEEE 1838 standard for 3D IC test. It's also important to generate and insert 1149.1 compliant tap for the entire package assembly so that we can actually test this part at the board level, at the true full board level, and it'll look like a regular chip. We want to shift left to the RTL phase as much as possible to implement DFT and IP test, and that gives us an early view of DFT for the physical design teams. And then we need to be very in phase with the multi-die and package level engineering teams to include the test bus planning and routing, the test timing, so between dies, functional and timing simulation reports, and wafer level die test and planning and validation. And then we'll generate die-to-die boundary scan-based interconnect patterns. We'll extract package level boundary scan or BSDL file that goes on to board test for board level testing. Then we'll create and insert an IEEE 1687 iJTAG network that we'll use to initialize the tests inside the part and actually run some of the tests inside the part as well. So this IEEE 1687 is used for both DFT and IP testing.
So it's obvious that DFT and test are critical for multi-die integrated designs and cannot be ignored or left as an afterthought. So what die and package level planning interactions do we need for physical design, power analysis, packaging, and test hardware to accommodate 3D, DFT, and IP test?
So one that jumps out right away is at WaferProbe, that KGD WaferProbe, we don't have the ability today, the technology there today, to build probe cards that have the fine pitch and reliability of a standard probe card for known good die testing. And the reason for that is that probe card has very tight spacing for micro bumps, which both 2.5D and 3D chips are using. It's much finer pitch than standard bumps. And so what we do to get around this is we put in something called sacrificial pads that are at standard bump spacing, and we can build a probe card that can probe those, provide all of the test required signals, and then be able to provide a sampling of power and ground. And we have to be very careful with that because if we don't get it right, we can end up burning probe tips. We can end up with excessive IR drop and noise. So we definitely need to be in touch with the power analysis and the thermal analysis and reliability. So reduced power and ground can actually cause false failures due to IR drop, and so you end up throwing away good parts, which affects your yield. We talked about the test hardware reliability due to the high current density at the probe pins, since we don't have all of the power and grounds available to us. And then we need to make sure that since the test patterns can have very high activity factor, we need to run both power and thermal analysis in all the test modes, both at the individual die and SIP level. Power control capabilities of the DFT tool should also be used. And as the aforementioned packet-based scan, if you have that capability. And then chiplet placement and alignment of the die-to-die test interfaces are important because the package team will provide that to us for use during SIP level physical planning process. So the DFT designers need to be interactively driving forward the test interface requirements and working with both the packaging and physical design teams. And then finally, support from the package team is also needed to generate the SIP level die wrapper netlist and parasitic extractions that are necessary to do die-to-die STA and timing simulation of the test interfaces. Those high-speed test interfaces may also require high-speed signal integrity analysis from the package design team as well.
So designing a fully testable SIP requires the design and test teams to collaborate as early as possible. What other factors do we need to consider for 3D test?
So designing dies for a system in package or multi-die architecture has to incorporate several DFT standards that can be effectively integrated in package into the SIP. And these standards include IEEE 1838, we talked about earlier, which is for 3D IC test, IEEE 1687, which is iJTAG, we use for die-to-die test initialization and getting results from DFT and IP core test. We also use that 1149.1 and 1149.6 for die-to-die interconnect testing for both 2.5D and TAP for I/O level boundary scan and IJTAG. For 2.5D, we actually doing board level boundary scan inside the package again. So that's a sort of a new capability. Specific IP test modes for those specific standards that we talked about, like UCIe, HBM3, OpenHBI, BOW, or others, need to be implemented into the functional SIP design. And then the die and test method compatibility is also important for SIP dies and chiplets from different process nodes that we talked about, may require special binning and storing of signatures inside OTP or eFuses. And also running full die level common functional and test interfaces are needed to be between the dies. So we have to make sure that we have the same interfaces between dies, or the two dies just won't talk to each other.
Now, we didn't talk much about 2.5D or 3D IP test. Can you say a few words about IP core testing?
Yeah, so what are IP cores? First of all, these are cores that you get from third-party providers. Now we have a new market for chiplets as well, which also might come from third-party providers. And in those chiplets, there might be things like SerDes, DDR, and HBM5. There might be PLLs, DLLs, and all of these need to be tested. So we can't leave test as an afterthought. So in the past, IP vendors often shipped their IP cores with just a Verilog test bench at the IP level, and then left it as a user exercise to map and cyclize those patterns all the way up to the top level. With 2.5D and 3D, you can imagine the additional complexity if we have that challenge. So this is essentially like adding a new level of hierarchy when we're doing 2.5D and 3D. We're adding kind of a hierarchy above the top level of the chip that's incorporating all the chips. And that's where that wrapper netlist comes in. So IP vendors are increasingly shipping their IP cores with IJTAG. And in the IJTAG standard, there's a couple files. The first is called ICL, or ICL, which is a hardware description of the test interface. And the second is called PDL. And the PDL is like a pattern description. And so if you ship these two files and you use commercial IJTAG tools, you have the ability to generate automatically all the way up to that top level of the SIP, the test benches and production test vectors that you need to get the part going. So that's a very important capability that is referenced in the 3D IEEE spec and is also its own specification called IJTAG. And then EDA vendors are also providing the IJTAG tools I alluded to that can take these all the way up to the top level through what we call retargeting. And then in other areas where IJTAG can help are things like loading large amounts of IP firmware. For example, a SerDes might have a microprocessor or something inside of it. And to initialize the SerDes, you have to load a bunch of pretty extensive amount of data over IJTAG and start it up inside the IP. And then other areas include things like calibration procedures for high-speed PHYs. And these can be shipped as standard building blocks for IP test while adding automation to what's already used to be a fairly manual process in the past.
We've had 7 other podcasts for other areas of 3D IC testing. Can you kind of talk and specify how 2.5D and 3D IC tests can be complementary to the other areas we've talked about?
Yeah, so first we talked about power and IR drop. But another area that's common in with some of the previous podcasts, like the reliability podcast, are things like burn-in testing and voltage stress. So burn-in is where we put a sample of parts into the burn-in oven, a special oven, and we raise the voltage and temperature to emulate many years of operation. So for example, we can keep the parts inside that burn-in oven for up to 2,000 hours. We can emulate like 10 years of life for that part, depending on the temperature that we have. During that time, we continually run all the package level SIP tests to provide some activity. And then we take the parts out at regular intervals to test them fully on a production tester or ATE to see if any of the parts fail. And so if any of the parts fail, then we do failure analysis. We go to the FA lab and get those parts fixed, find out what happened and correct it. So reliability testing is part of that. Another one is voltage stress. It turns out that doing a voltage stress with the right voltage level for the right duration and the right ramp time can pretty closely emulate burn-in, and it has the ability to do that in just 100 milliseconds or so of production test. And so you can actually do it during the production test itself. It gives you a chance to sort of degrade or destroy parts that are marginal that might fail later on. So voltage stress is good as well for reliability testing.
Thank you, Joe, for the highly informative discussion on this 8th podcast of 3DIC. We're looking forward to future podcasts with you on the same topic. Do you have any final thoughts for our audience?
Well, thanks, David, and thanks to all of our listeners for participating in our 3DIC podcast. You can access the rest of our series for other interesting discussions about many other topics, including packaging power and reliability.
Wonderful. Thank you, Joe, and we'll talk with you next time.
Thanks so much for your time.